This is a redo of class from last week. We had a computer problem, so I wanted to redo the recording. So last time we talked about graphs, but I might as well just start from the beginning of graphs to make this a fluid lesson. So first of all, let's just define what a graph is. So a graph is, you can think of it as some sort of special set that contains two types of sets. It contains a set called a vertex set and a set called an edge set. So it's defined by these two sets. So what is the vertex set? It's a countable collection of vertices or points. I even call them dots. So these are just points in the plane, you can think of it. So usually, I mean, for our sake, they'll be finite. So we might write it, our vertex set, like v1, v2 to vn. Or if you maybe know exactly how many vertices you are, you might just use like A, B, C, something like that. So with the vertex set, we also assign an edge set. So in the edge set, the elements in the edge set are going to be pairs of vertices. So what defines the pair is that if you have a pair VI, VJ that's in the edge set, what does that mean? That means that VI, the vertex VI, is connected to the vertex VJ by an edge. So obviously you can't have edges with vertices are not in the vertex set. Right? So the vertex set needs to be assigned to edges. Of course, you can have vertices that don't have any edge. That's fine. It does not restrict that. So that's all in edges. It's pairs of vertices. So when you get to specific types of graphs, based on how you define edges, there's something called a directed graph, where the order of edges matter. So this means that if VI, VJ is in the edge set, you can also have VJ, VI. So these would be two different edges. So what does that mean? If you have VI and VJ, this might be this edge, VI, VJ, but maybe going in the opposite direction would be VJ, VI. So for our class, we'll only be focusing on non-direct graphs. So we won't have this distinction between left and right. So in our case, VI, VJ is the same as VJ, VI. Oops. Okay, so another distinction we want to make is is something called a simple graph. So what is a simple graph is also how you define edges. So in a simple graph, you want to have no loops. So what a loop is an edge set where the two vertices are the same. So we don't want this. So this is going is not going to be on our edge set. So loop is edge with same vertex ends. And we also have no multiple edges. So a multiple edge is that if you could have vi vj and another vi vj. So like if you have vi vj, so it's different from directed, but it's just two different ways of getting there. And a loop is like, so in our, for a simple graph, we want to have no loops and no multiple edges. So if you see a Vij, so for simple, Vij is unique, and Vi is just not going to be in the edge set. Okay, so that's a simple graph. And this is what we'll be focusing on. Okay. Another problem in graph theory, which is actually an open problem, is it's called the isomorphism problem for graphs. But first, let's just say what an isomorphism is. So two graphs are isomorphic. And you can probably just guess the definition just based on the name. Iso means same, and morphic is like a transformation. So two graphs are isomorphic. Sometimes we say GI or G1 equals swiggle equals sign swiggle G2 if you can relabel vertices in V1 to vertices in V2, and same with edges. So edges in E1 can be relabeled to edges in E2. So maybe an easier way of saying this is that isomorphic, if you can maybe twist and stretch one graph into the other. So let's just give an example. So here is going to be a couple isomorphic graphs. So here's a graph. Here's V1, V2, V3, V4. So the vertex set is V1, V2, V3, V4, and the edge set. So V1 is connected to V2, so that's in the edge set. V1 is connected to V3. V2 is connected to V3. And V3 is connected to V4. So that's the edge set. And I'm going to draw a different graph. Let's do this graph. And maybe they're A, B, C, and D. So our vertex set is A, B, C, D. And our edge set is A, B, A, C, B, C, and C, D. So what makes these graphs isomorphic is that essentially they're the same graph, right? I just maybe twisted one graph to get to the other. So maybe like this like triangle, shape part of the graph, and maybe stretch out and make into a circle. So that makes A, B, C. And then the V4 edge, I just maybe, pick it up and, rotate it inside. And that makes the D inside that circle. So what is the relabeling is that, well, let's think about what relabeling would be. So V4 can only be relabeled to D, right? It's kind of that distinctive. There's no other vertex like that. So V4 would be matched with D. And that implies that V3 would be matched with C. Now there's a choice whether to make V1A or V1B and vice versa for V2, right? It doesn't really matter because I could kind of twist this circle around to make, to essentially swap the places of A and B, just kind of like reflecting it. So there's more than one choice to make, but the fact that you can make a choice implies it's isomorphic. So V2, we can just choose to be matched with B, and V1 can be matched with A. So, and then just to note, V2 could be matched with A, and V1 could be matched with B. So that implies there's maybe another isomorphism that you can create, but the fact that you can create one, so the isomorphism is this kind of correspondence between edges and vertices. There's more than one that you could make, but the fact that you can make one implies the graphs are isomorphic. So you can imagine that, like maybe for a small number of vertices, this is pretty easy to do, right? Just kind of look at it and see if they're isomorphic. But for large number of vertices and edges, this becomes a harder problem. And as of right now, or at least from what I remember, this is an unsolved problem to have an algorithm to determine if two graphs are isomorphic. But one thing that we can do is we can kind of consider some necessary conditions for two graphs to be isomorphic. So if you recall when you're discussing these identifications between vertices, one thing that we said was that, well, there's only one vertex that's like V4, which is D. And why is that? It's because, well, D and V4 are the only ones with only one edge adjacent to it. And by similar reasoning, there's only one vertex like V3, and that's C, because C and V3 are the only vertices with 3 edges adjacent to it. So what we can do is we can store this information about what vertices are adjacent to which vertices. We can store this information in a matrix. So let's talk about the adjacency matrix. So the adjacency matrix for a graph, let's say the adjacency matrix of a graph is going to be it's going to be a square matrix with the dimensions with the number of vertices. And we're going to define the entries by let's say, so the ijth entry is just going to be a 0 and a 1. Where we're going to put 1 if vi is connected to vj, so they're adjacent, and put a 0 if they're not adjacent. So so let's just do an example from the last time. This is v1, v2, v3, v4. There are 4 vertices, so the dimension is 4 by 4. And we're going to put, we're going to fill in the matrix based on what's adjacent. So this first entry here, is v1 connected to v1 by an edge? No, right? And that'll never be true because we're thinking about simple graphs. Is v1 connected to v2? Yes, it is. Is v1 connected to v3? Yes, it is. But v1 is not connected to v4, so that's a 0. Now for v2 is connected to v1, so that gets a 1. v2 is, there's no loop, so it's 0. v2 is connected to v3, but it's not connected to v4. So now for v3, it's connected to v1, to v2, not to itself, and connected to v4. And v4 is only connected to v3, so it only gets a 1 in the v3 position. So that's the adjacency matrix. So one thing you can notice, just based on the definition, is that for simple graphs, for simple non-directed, so first of all, what does the non-directed tell you is that the adjacency matrix is symmetric, right? And that's because if vi, vj is in the edge set, well, if it's non-directed, well, vi, vj is the same as vj, vi. So these are the same. But so if vi, vj is in the edge set, then that gets a 1, and then vj, vi gets a 1. And similarly, if they're not in the edge set, then they would not be connected. So this implies that the ij entry, it will always be equal to the ji entry. So that implies it's symmetric. And for simple, there'll always be zeros in the diagonal. Right, because vi is never in the edge set. So, you have a symmetric matrix with zeros in the diagonal and just 1s and 0s, and that's the adjacency matrix. So now what you could do is, so you can create an adjacency matrix from the graph, and you also can go in the reverse. If you have a matrix that satisfies adjacency matrix, then you can construct what the graph would be. So one thing about symmetric matrices is that you can construct them pretty easily. If you know, for example, if you know what the first row is, let's just make up something. Let's say this is our first row. Well, if it's symmetric, that means that this first row must be the first column as well. So constructing a row automatically constructs a column. So let's just fill in some random numbers for the rest of the matrix and see what the graph would look like. Okay, so the dimension is 5 by 5. So there's going to be 5 vertices. So now let's take this first line. This means that V1 is connected to V2 and is connected to V3 and is connected to V5. So V2 is connected to V1, we already did that. Is also connected to V3, is connected to V4, and is connected to V5. So now V3, we already took care of V1 and V2, and we also have it connected to V5. And now V4, we had it connected to V2, but that's the only thing that's connected to because everything else is 0. So now V5, same thing. It's connected to V1, V2, and V3, but it's not connected to V4. So this is the graph. So you can construct a graph from the adjacency matrix. So now one thing to notice is that isomorphic graphs may not have the same adjacency matrix. So why is this? Is because, well, so look at V4. So V4 was a vertex that was only connected to one other vertex. But what if I made this V1? What if I called this V1? That means that this this row with only one entry of 1 will be in the first row and automatically have a different graph. And this row might look different as well. So so one thing to note, when you do your work and you compare your work with someone else, you might have different adjacency matrices, and that's fine. But one thing is that the graphs from even different adjacency matrix, as long as it's it gives the same graph, they'll still be isomorphic. So just be aware that if your matrix looks different from someone else, that doesn't mean it's wrong. Some things that must be true. The number of ones should be the same. One thing that's interesting to note is that if you add up the number, if you add up the elements in a row, you get the number of edges coming out of it. That vertex. So for example, if I add up 1, 2, 3, I can see I have 1, 2, 3 edges coming out of it. So sometimes this is called the valence. Valence of a vertex. Meaning the number of edges emanating from a vertex. So you can think of the adjacency matrix as a matrix that gives you the valence of every vertex. Okay, so thinking more about isomorphic graphs, let's think about when graphs are not isomorphic and how we could tell. So I'm going to construct 2 graphs. And we can see whether or not isomorphic. Okay, so let's see why these two graphs are not isomorphic. So on the one hand, they have the same number of vertices and the same number of edges. So you might think, well, it's a possibility that they could be isomorphic, or that is a necessary condition. They must have the same number of vertices and edges. But it turns out that these are not isomorphic. So first of all, it's probably clear where it would fail isomorphism is there's this diagonal that's different. But really the question is, why is it so different? So it's kind of like, let's assume that they are isomorphic, kind of fill in the gaps of why this fails isomorphism. So based on kind of the reasoning that we did for the first pair of graphs, let's think about some vertices that must be labeled the same. So first of all, let's just give names to all these. So usually when doing these isomorphisms, I like to use V subscripts and then like ABC. I don't like to use like W because I could get confused with kind of the subscripts. So based on our first pair of isomorphic graphs, we have the similar phenomena that V7 and G are the only vertices that only have one edge coming from it. So if you were to look at the adjacency matrix, row 7 would only have one entry. Same with whatever row G would be. So first of all, that V7 must be connected to G. So based on that, well, since it's only connected to one other vertex, the thing it's connected to must be equivalent if this is isomorphic. So V6 must be connected to F. And now, what's another kind of unique vertex? We have this this vertex where this diagonal meets V2 and E, right? V2, and why is it different from V4? Is that V2 has 4 edges coming out of it, and E has 4 edges coming out of it, whereas A has 3 and V4 has 3. So V2 must be connected to E. So there's a problem here. So this causes a contradiction. And why is that? Well, F is connected to E, but V6 is not connected to V2. So immediately this is a contradiction. So what's one way we can talk about this? We can talk about this based on a problem with not even from adjacency from V2 to V6. We can think of this as the length of a path from V7 to V2 or from G to E. So if you think about it, there's a I can get from V7 to V2 by a minimum number of 3 steps. But I could get from G to E by a minimum number of 2 steps, right? So automatically that should tell you that these things are not isomorphic. So that'll help us a lot in determining when things are not isomorphic is path length. So, so let's define what a path is. So path is a sequence of adjacent vertices. So by adjacent, I mean connected by an edge. So for example, the path from V7 to V2, there's a couple of them. So V7 to V2, here's one path, V7, V6, V5, V2. Here's another one, V7, V6, V3, V2. Here's another one, V7, V6, V5, V4, V2, and maybe one more, V7, V6, V5, V4, V1, V2. So the last one takes a bit longer to get there, but it's still a path to get there. So you can also describe these as a sequence of edges. This one might be easier to talk about. And it's, if you have the sequence of vertices, it's a little bit easier. It's easy to construct what the edge sequence must be. So edges are just adjacent vertices. So it's V7, V6, V6, V5, V5, V2. So why is this maybe nice is because when you talk about path length, it's the number of edges in the sequence, in the path sequence. All right, so, so that's path length. So the idea is that isomorphic graphs must preserve path lengths between vertices. So all these paths that we constructing from V7 to V2, under some correspondence of vertices, that must also be a path between G and E. So maybe one of them doesn't work. Well, we know one of them doesn't work, right? There is no length 2 path. So the path that says G, F, E, there is no path that corresponds to that path. So that's another way of seeing the contradiction. Okay, so we can actually use the adjacency matrix to help with thinking about path lengths. So let's redraw these pictures, or at least one of them. Well, I'm gonna do the right graph. Actually, I'll do both. Okay, for this right one, I'm going to focus on thinking about from G to E, how many length 2 paths are there? So one thing to think about about length two paths, what must be true about a length two path? So length two path must have the property that, like if I have G and E, and if there's a length two path, say V, that this kind of intermediary vertex must be connected to both G and E. So this vertex here, that VG needs to be in the edge set and VE needs to be in the edge set. That's a necessary condition for there to be a length two path. So, well, we know what these things are in the adjacency matrix. This would imply that, let's just say A for the adjacency matrix, that AVG would need to equal 1 and AVE would need to equal 1 at the same time, right? But let's suppose there's a vertex W that's connected to G, but it's not connected to E. So we know that there cannot be a length two path. So how does this work in the adjacency matrix? Is that AWG is equal to 1, but AWE is equal to 0. So if we want to add up the number of length two paths, what we could do is just say, let's just multiply the entries. If AVG times AVE is equal to 1, then there is a length two path. However, if AWG, AWE is equal to 0, there is not a length two path. Notice this also takes into account of the case where you have a vertex that is not connected to G or to E. Right, this would be AZG is equal to 0 and AZE is equal to 0. So this also implies the product is 0. So let's try to do this in general and with some index numbers. So let's think about, let's just use this graph now. The number of length two paths. Let's do one that's a bit interesting. From V4 to V5. And let's look at the adjacency matrix. All right, so the adjacency matrix, based on this configuration, be 0, 1, 0, 1, 0, and then 0, 1, 1, 1. Wait, there's 7 of those. Okay, we have 1, 0, 0, 0, 1, 0. So before B5, B6, and B7. Okay, so big adjacency matrix. Okay, so if I want to think of length to paths from V4 to V5, well, let's look at, let's add up all the entries based on this configuration here. So, so I want to look at edges that are vertices that are adjacent to V4. And I will also want to look at edges that are adjacent to V5. Notice the rows and columns are the same, so I could just choose one to be a row, one to be a column. And for reasons we'll talk about, that hopefully maybe we'll see. Okay, so if I look at a 4, 1, so now I'm going to look at vertex 1. Here's V4, here's V5, and here's V1. So I want to look at A 4, 1 times A 5, 1. And I'm going to say this as 1, 5, reasons you might see. Okay, so in this case, 1 is connected to V4. So it's 1, but 1 is not connected to V5, so that's 0. So we'll do this for every single vertex. So let's do A 4, 2 times A 2, 5. So I have a 1 times a 1, and let's look at, is there a length to path? Yes, it's this one, V2 to V5. So we're gonna do this for every single one. A 4, 3, A 3, 5. So what is this? 4, 3 is 0, 0. A 4, 4, that's always going to be 0. So, and then A 4, 5, that's also always going to be 0. Well, 4, 5 is not 0, but the product is 0. Okay, A 4, 6, A 6, 5. So that's a 0. Even though 6 is connected to 6 connected to 5, yeah. So it still gets a 1, but the product is still 0. And we have A 4, 7, A 7, 5. So they're both 0. All right. So how many length to paths are there? Well, there's just one. Okay, this was the one up here. V4 is connected to V2. It's connected to V5. However, if you look kind of closely, so if you sum up all these entries, you'll get the number of length to paths. So on the right-hand side, it's 1. Now on the left-hand side, we can actually express this as a sum. So notice that on the first entry, I'm looking at the 4th row. That's why I circled this row in that column. So it's always going to be A4, but there's going to be a changing index, so A4K. And the second thing in the product, I'm always looking at the 5th column, AK7. So this should look very familiar to you. This is matrix multiplication. So, so let's define that. So, so if if A is the adjacency matrix for G, A squared collects the number of length 2 paths. So in other words, if I'm looking at the ijth entry of A squared, it's the number of length 2 paths from Vi to Vj. And again, just to see that based on the math, it's the sum from k equals 1 to n of Vik, Vkj. Right, you're looking at the adjacencies, or not V, because you're looking at the adjacencies of, maybe use capital, of Vi and the adjacencies of Vk. All right, so if you think about it, if we multiply it one more time, A cubed, if you think of it as A squared times A, what you're counting up is your length 2 paths, and then you're checking for an adjacency. So in other words, I have, let's say Vi, and I have Vj here, and I have marked a length 2 path from Vi to Vk. And let's say there's, I don't know, 2 of them. I'm multiplying by 1 or by 0 if there is a connection from Vk to Vj, right? So this is just multiplying by 1 or 0. So if there's no connection, then there's no length 3 paths. If there is connection, then there is one length 3 path. And you do this for all vertices. So A3, A cubed, counts the number of length 3 paths from Vi to Vj. Okay, so let me do an example, maybe lower dimension. Okay, let's use the let's see. Let's use let's see. Let's just compute the adjacency matrix and its and higher powers. Okay, so A, using this setup, 0, 1, 0, 1, 0, And then that. So that's your adjacency matrix. Now let's square this. Okay. So, so for the first entry here, I would get 2. So just, imagine another matrix here. Might as well just draw it out. 1, 0, 1, 0. So, I mean, although there's a lot of multiplication going on, it's all ones and zeros, so it's not too bad. So first entry is 2, and then so one little trick you can see is that since the columns are equals to the rows, is that if you multiply, so the diagonal entries will be equal to the valence. Right? If you multiply for the third row and third column, since entries are the same, you will always be getting a 0 times 0 or a 1 times a 1. You'll never get a 1 times a 0. So the diagonal entries of the square will always be the valence. And why does that make sense kind of intuitively? What are the length 2 paths from a vertex back to itself? Well, you can go along an adjacent edge, and then you can just come right back. So you go along an adjacent edge and come right back. So even just not even doing multiplication, but just looking at the picture, you can tell what the diagonal entries will be. So it's 3, 2, 4, and 0. Oh, sorry, 1. It'd be 0 if there wasn't an edge. Okay, so let's continue. All right, so this one would be a 1. Then we have 2. And a 1. And a 0. So second one, a 1. 2, a 1, and a 1, and etc. So you do the rest. So let's just tell that this will mark for you the number of length 2 paths. So what does this entry say? This says the number of length 2 paths from V1 to V3. So maybe we can see that by the picture. So you can either go from V1 to V4 over to V3, or you can go from V1 to V2 over to V3. So yeah, that's it. So the powers of the adjacency matrix can tell you a lot of information about a graph. And if you think about it, if you have 2 different graphs and calculate the powers, so all the numbers should be the same. So again, the matrix may not be the same because of based on choice of vertices, but the idea is that powers would need to have the same numbers at least. So for example, like there should be a row with 2, 1, 2, 1, 0 in any graph, adjacent square of an adjacency matrix of that's isomorphic. So yeah, that takes care of the powers of the adjacency matrix. So that's really it about graphs. And then so we're going to move on to 1.5, which based on when this will go up, will probably be tonight, which will be about seeing how matrices can correspond to row operations. And one thing I'll do just to see that, to help see that, is think about doing matrix multiplication. You can think of it as you can think of a matrix as a column of rows. So when you do this multiplication, you get A row 1 plus B row 2 and C row 1 plus D row 2. So this actually works out if you replace this with like X, Y, Z, W. It's AX plus BZ and AY plus BW, CX plus DZ, and CY plus DW. So first of all, what is row 1 is XY, and so if you think about it, you can kind of group these elements together and group these elements together, and you get A times XY plus B times the vector B, or what is it, ZW. And similarly, you have C times XY, and then D times ZW. So this actually might help calculation a lot easier, for your own matrix multiplication. But another thing is try to come up with A, B, C, D that do the row operations. Like what should A, B, C, D be to get maybe row 2, row 1, to get alpha row 1, row 2, to get row 1 alpha, or row 2 plus alpha row 1. Right, these are the row operations. It turns out that they're pretty simple, but we'll do this for the next class. So these are, again, row swap, multiply a row by a constant, and then multiply a constant times a row to another row, and add it to another row. All right, so so that is about graphs and some stuff that we'll do later. Sorry again for the mess up of the class last time, but hopefully this will be useful. All right, that's it.